Okay, so for the how-to, I'm going to pose a question first, and that question is first. A tank has pure water flowing into it at 10 liters per minute. The contents of the tank are kept thoroughly mixed, and the contents flow out at 10 liters per minute. Initially, the tank contains 10 kilograms of salt in 100 liters of water. How much salt will there be in the tank after 30 minutes? So for a general setup of how do we approach mixing problems, this is very typical in like your givens. So for halves, what do we know? We know the rate in, and we know that it's pure water. So it'll tell us, is the water flowing in? Is it salt water? Is it sugar water? Is it chemical water? But here it's pure water, so we know the concentration going in. We know that the contents of the tank are kept thoroughly mixed. That's the assumption that the contents of the salt are even throughout. And the contents, meaning the water, flows out. So we have a rate out at 10 liters per minute. We're also given that initially how much initial amount of substance. So this is helpful because this is going to help us out with the initial value problem aspect of mixing problems. And then what do we want? We want how much salt will there be in the tank after 30 minutes. So we need a function to give us the amount of salt in the tank at any time. And since that's what we want, it makes sense to define it. So let Q of T equal the amount of salt dissolved in the tank at time T. We'll say in minutes since everything we're given is in minutes. All right, so how do we get Q of T? Because we want Q of 30. Well, looking at my givens, my halves, I have rate in, concentration in, rate out. Rates make me think of derivatives, which makes me think of differential equations. Since I want Q of T, if I'm thinking about differential equations, I know that dq dt, if I separate this and then integrate both sides, I will get back to Q of T. So that's very helpful. Let's remind ourselves that dq dt is the rate at which the amount of substance, or in this case the substance is salt, is changing. So we can come up with an expression for the rate at which the amount of substance is changing because we're given the rate in, the concentration in, the rate out, and the initial amount of substance. So in general, for any problem anywhere, not just for this one where we're talking about salt, the rate at which the amount of substance is changing has to do with flow in minus flow out. So the rate at which the amount of substance is changing. So flow in. If we have water with salt flowing in, then the rate at which the amount of substance is changing is going to first depend upon the rate of substance entering times the concentration of substance. Because if we're pouring salt in, well, then the rate at which the amount of salt in the tank is changing, that's going to depend upon the rate at which we're pouring salt in. But if water is leaving the tank, or if salt is leaving the tank, the amount of salt in the tank is also going to depend upon that rate, that flow out. So the rate of substance leaving times concentration of substance leaving. So this right here, this generic dq dt is going to be really helpful for all of our mixing problems. And there's another aspect of this equation that we can generalize, and that is this concentration of our substance leaving. Now, if you just scoop up a glass of water out of this salty water tank, then the concentration of the substance that you get should be Q of T, the amount of salt in the tank, divided by, so the amount of salt total. Concentration is amount over, well, how much water is there? So total liquid. We defined Q of T to be the amount of salt in the tank divided by the amount of liquid in the tank. And this is going to be really helpful when we are setting up our mixing problem. All right, I think we have everything we need for our next step, which is to attack the problem itself. So, if you need to, pause, because I'm about to put this on the side so that you can see this. Okay, so we're gonna repeat the problem. A tank has water, pure water, that's important, pure water flowing in at 10 liters per minute. So I'm gonna draw this scenario. I've got a tank, rate in 10 liters per minute, concentration in is 0 kilograms per liter. Because I'm looking at my general equation, I'm saying, okay, I need the rate of the substance entering and the concentration. I now know that concentration is 0 and the rate is 10 liters per minute. The contents of the tank are kept thoroughly mixed. Okay, that's always the case. And the contents flow out, so rate out at 10 liters per minute. Now, what is the concentration out? This is a little bit trickier. Here we said, well, it's the amount of salt in the tank, that's Q of T, divided by the total amount of liquid, total liquid. So what is the total amount of liquid? Well, let's come back to that in just a sec. Initially, the tank contains 10 kilograms of salt in 100 liters of water. So we know this is our initial value. And this is the initial value of salt, initial amount of water. So this tells us that Q of 0 equals 10. And this is going to help us here for our total liquid. So we know that our total liquid is 100 liters plus we have water flowing in at a rate of 10 liters per minute, so 10 T. So every minute we get another 10 liters minus Well, each minute, 10 liters also flows out, 10t. So we have Q of t over 100 plus 10t minus 10t. And now you might be asking yourself, well, Ms. K, do I really have to do this part since this just equals 0? And my answer is yes. I want you to think about it because not always are rates in going to be equal to rate out. I might be pouring water in at a faster rate or leaking water out at a fast rate, and that's really important to consider. Okay, next piece. So we have rate in, rate out, concentration out. Now we can set up our differential equation and start to do some calculus. So we know that dq dt, the rate at which the amount of substance is changing, is equal to the rate in times the concentration in minus the rate out, 10, times the concentration of the liquid leaving out. So Q of T over 100 here. So 10 times 0 is 0, so we have dq dt equals negative 10 Q of T over 100. Let's simplify that even more because that will be helpful. Negative Q of T over 10. From here, it becomes a separating variables problem. We want Q of T to go with dq and dt to go with negative 1/10. So I'm going to move this over to, we'll have 1 over Q of T dq equals negative 1/10 dt. We are going to integrate both sides. Natural log of Q of T equals negative 1/10 t plus c. Gotta have one side with the plus c. Now to undo that natural log, we're gonna take both sides, raise them here, e to the power of natural log. This undoes us. We have Q of T is equal to e to the negative 1/10 t plus c. Well, we know this piece right here can be rewritten as e to the negative 1/10 t times e to the c using our exponent properties. This is just a constant, so this can be rewritten as c e to the negative 1/10 t. So Q of T is equal to c times e to the negative 1/10 t. That's a generic equation. Now a reminder that our goal was how much salt will there be at 30 minutes? Well, we can't plug in t equals 30 yet because we still have this c. Well, how can we find c? Let's remember that we were actually given an initial value. Q of 0 equals 10. We'll plug those values in and we'll solve for c. So Q of 0 equals 10, c e to the negative 1/10 times 0. E to the 0 is 1. 10 equals c. That wasn't too bad. Sorry, I went off the screen there. So we know then that Q of T is equal to 10 e to the negative 1/10 t. Now we can go back to find out how much salt will there be 30 minutes in. Q of 30 equals 10 e to the negative 1/10 times 30. 10 e to the negative 3. So, since we are in context, how much salt will there be? There will be 10 e to the negative 3 kilograms of salt at 30 minutes in the tank. So again, what we did is from the context, we determined our rate in, our concentration in, our rate out, our concentration out. What does this mean? It's giving us an initial value of salt, an initial value of water, initial amount of water, which helped us find the total liquid in the tank at any given moment so that we can get that concentration out. Then we used our generic formula of the rate at which the substance is changing is dependent upon the rate at which the substance is entering minus substance leaving. Both of these multiplied by their own concentrations. So we took that generic formula, plugged in what we know from our context, separated variables, integrated, plugged in our initial value here so that we can get C, and then find the specific time it's looking for. I will be back after school around 3:45, so if you have urgent questions, please stay and ask. Enjoy the mixing strippies. See you in a little bit. Goodbye.